Hello everyone. This video is titled Finding Laplace Transforms Using Basic Formulas. So in this video I'm going to be taking you through a table, just one page where I show you the Laplace transform for your basic functions, polynomials, exponentials, and trigonometric functions, and talking about also how the Laplace transform is a linear transform, has the linearity property, and use all that information to help us in finding the Laplace transform of certain functions. Right, I've got 4 examples for you in this video. And using these transforms of basic functions and the concept of linearity, we're going to find the Laplace transform of some functions, without actually using the definition, with that integral from 0 to infinity of e to the negative st times f of t dt. Like, we're not doing all that this time. So let's take a look. All right. So first, we've got a list here of transforms of basic functions. Now again, I want you to recall the definition. I just said it out loud a second ago. That the Laplace transform of some function of t was equal to the integral from 0 to infinity of e to the negative st times that function f of t with respect to t. Right? Now, you could use this definition to verify all 5 of these in my list here, but I'm not going to actually write that out. I'll leave that to you. Use the definition to verify the following. First, the Laplace transform of just 1 would be 1 over s. Remember, the Laplace transform ends up being some function of s only. Same here, the Laplace transform of a polynomial t to the nth power is the power factorial, so n factorial divided by s to 1 higher than that power, s to the m plus 1. For exponential functions, the Laplace transform of e to the alpha t or e to the at is 1 over s minus alpha, or s minus a. The Laplace transform of the sine of a multiple of t, right, say the sine of kt, ends up being k divided by s squared plus k squared, where k is a constant. K is some constant here, some number. And then something very similar for cosine. The Laplace transform of the cosine of kt is s over s squared plus k squared. So they got the same denominators as, that constant multiple is in the numerator of the Laplace transform for sine, and then s itself is in the numerator for the Laplace transform of cosine. So again, I would recommend memorizing these, especially if you're in the middle of a differential equations course. Make things a lot faster, a lot quicker for you. And I'll tell you right now, if you have these memorized, it'll be a lot faster to find the Laplace transform of certain functions instead of going to the definition every single time. All right, and then one more thing I want to point out is that the Laplace transform is a linear transform, meaning if you take the Laplace transform of a linear combination of functions, you get that same linear combination of the Laplace transforms of those functions. So you can basically go term by term and pull out constants. All right, so the Laplace transform of a times f plus b times g is equal to a times the Laplace transform of f plus b times the Laplace transform of g. All right, so you can just go kind of term by term, pulling out constants and taking the Laplace transform of each term that way, of some linear combination of functions. Alright, so again, I'm going to refer back to this, but I would recommend memorizing at least these 5. I mean, you might find some tables in other texts with other functions as well in a list of transforms of basic functions, but I'd recommend memorizing at least these, all right, for now. Okay, so now for the rest of the video, I'm going to find the Laplace transform of some function using those formulas that I just covered up. So the Laplace transform of 2 times t to the fourth. Well, you can pull, that's only a single term. You can pull the constant out. It'd be 2 times the Laplace transform of t to the fourth. And if you recall from the earlier page, when I have a power of t like this would be 2 times, and then the Laplace transform of t to the fourth, recall from again this page here, would be 4 factorial in the numerator. 4 factorial over s to the 4 plus 1. So s to the 5th power. And then we simplify this. Okay. Now 4 factorial, right, that's 24. 2 times 24 is 48. So this would be 48 over s to the 5th power. I'm sorry if my 5's and s's look similar, but this is s to the 5th power. And there we go. This is, that was little f. So this is capital F of s, right? Our Laplace transform of 2 times t to the fourth. Okay. Great. Let's go again. So again, I'll keep referring back to these. Hopefully, eventually, you'll have them memorized. Next one. Function this time, f of t, is the quantity t plus 1 to the 3rd power. Now I can't do linearity here. This isn't a sum of a bunch of terms. I have to expand this. Now t plus 1 cubed, you can do this for yourself. Do t plus 1 times t plus 1 times t plus 1. Or if you remember the binomial theorem, you got t cubed plus 3t squared plus 3t plus 1. That's the expansion of t plus 1 cubed. So then the Laplace transform of this function is going to be the Laplace transform of t cubed plus, and pull the constant out, 3 times the Laplace transform of t squared plus, and pull the constant out, 3 times the Laplace transform of t to the first plus the Laplace transform of 1, right? Just using that linearity property, going term by term, pulling constants out. And then all these use basically the same rule I just used. It'd be 3 factorial. The Laplace transform of t cubed is, the power factorial divided by s to that power plus 1. So divided by s to the 4th. Again, it's right here. Right. Plus, and then 3 times, and then again, the power of t, that'd be 2 factorial divided by s to the 2 plus 1, s to the 3rd. Plus 3 times, this is t to the first, so 1 factorial divided by s to the 2nd. Plus, and then this is just, now you could also think of 1 as t to the 0 and do 0 factorial, which is 1 over s to the first, which is, just 1 over s, which I already wrote down here. So actually, this first rule I have is a special case of this rule when n is 0. Alright, we simplify a bit. So this is 6 over s to the 4th. That's 2 times 3, that's another 6 over s cubed plus 3 over s squared, then plus 1 over s. And this is totally fine. I have a function completely dependent on s now. There's the Laplace transform of our original function. Totally fine to leave it that way. Now if you want to get a common denominator, be my guest, but I'm not going to do that here. Alright. So again, pretty simple so far, hopefully. So far I've only dealt with some polynomials. Here's one with exponential functions involved. So I'm going to be making use of this rule. The Laplace transform of e to the alpha t is 1 over s minus alpha. But again, I got to do some expansion. I got to write this out as a sum of a bunch of terms, not some quantity squared. So you have 1 plus e to the 2t, that quantity squared, that'd be 1 plus, and then 2e to the 2t, plus, and then e to the 2t squared, or e to the 4t. All right, so there is written out as a bunch of sum of a bunch of terms. Something I can apply the linearity property to, right? I couldn't apply the linearity property to this one. So the Laplace transform of this function. So again, going term by term, is just the Laplace transform of 1 plus 2 times the Laplace transform of e to the 2t plus the Laplace transform of e to the 4t. All right, now we already saw the Laplace transform of 1. That was 1 over s. Plus 2 times, now the Laplace transform of e to the 2t would again be 1 over s minus 2, right? Alpha is 2 here. So this would be 2 in the numerator over s minus 2. Plus, and then the Laplace transform of e to the 4t would be 1 over s minus 4. And again, now I have a function totally dependent on s. If you want to get a common denominator, put things together, be my guest, but I am not going to do that here. There's the Laplace transform of the function we were given. Right, very quick and easy, again, without using the definition, right, without taking that integral from 0 to infinity of all that junk. Right. Okay, and I've got just one more example here. Now this one's already written out as a linear combination of functions. I can go term by term already. I can apply the linearity property. So here I have a polynomial and a trig function. So here f of t is 4t squared minus 5 times the sine of 3t. So the Laplace transform of this function, just going term by term and using the linearity property, would be 4 times the Laplace transform of t squared minus 5 times the Laplace transform of the sine of 3t. Alright, so we have 4 times, now the Laplace transform of t squared, remember those powers of t, that would be 2 factorial over s to the third. Alright, 2 over s cubed. Minus 5 times, and then again, go back to this, the Laplace transform of the sine of kt, so here k equals 3, would just be k over s squared plus k squared. So this is going to be 3k over s squared plus k squared. Right. And then simplifying a bit, this is 4 times 2 is 8 over s cubed minus 15 over s squared plus 9. And there you have it. There's the Laplace transform of the function we were given, then very quickly, very easily, and without having to use the definition, without having to use some crazy integral. All right. Now I guess I know I said there before examples. Here's a fifth one. Here's a fifth one where we might have to use some sort of identity to get one of these basic functions to show up. All right, here's another one. So f of t equals the sine of 2t times the cosine of 2t. All right, now notice here I can't use linearity. This isn't the sine of 2t plus the cosine of 2t. So I can't apply linearity here, but I can do this using a trig identity. Sometimes you might have to with the trig functions to get a simple sine of something times t or a simple cosine of something times t involved. So using an identity, a trig identity that you should hopefully remember. Remember the sine of 2t times the cosine of 2t, that's half of the sine of 4t. Remember the double angle formula. The sine of 2 theta was 2 sine theta cosine theta. Well, just replace theta with 2t, and you've got what I have up here. All right. This if sine 2t cosine 2t times 2 would be the sine 4t, so you cut that in half. And now I have a very simple sine of kt involved. Sine, these Laplace transform formulas I'll show you are sine of kt to the first power, not sine squared or anything. Cosine kt to the first power. So that's exactly what I have here. So the Laplace transform of this function is just a half times the Laplace transform of the sine of 4t, which again, k equals 4 here. So this would be half of k, 4, divided by s squared plus k squared. Right, s squared plus 4 squared. And so what I'm getting here now, half of 4 is 2. We have 2 in the numerator, and then s squared plus 16 in the denominator. And there's your Laplace transform of this function sine of t, 2t cosine 2t. Alright, so just pay attention to, sometimes with the trig functions involved, you might have to use some sort of trigonometric identity to write the function in another way that's more conducive to easily figuring out the Laplace transform. Alright, so I know I said at the top of the video I had 4 examples, but I actually ended up doing 5. Right, 5 examples there. And hopefully watching me go through these, and as I said earlier, please try to have these memorized, make it a lot easier for you. I didn't do a cosine one, but all that changes is the numerator becomes s instead of k. Right? So just pay attention. Hopefully watching me go over these and memorizing this list will help you out when you're working on problems like this on your own, right? Finding Laplace transforms of some pretty, some linear combinations of some basic functions, polynomials, exponentials, and trigonometric. All right, and thank you very much for watching.